And I'm going to talk about three very important applications. I got started with the web last time, and I'm going to continue with the web. And then I'm going to talk about DNS, the domain name system, and then content distribution networks. And you can see the acronyms are upon us already. You know, we have www, DNS, CDN, and unfortunately, there'll be many more to come. But hopefully, you know, each one will be easy to explain. But before I do that, I wanted to go into something that I should have talked about, but actually makes a little bit more sense talking about now, which is we talked about tin cans and strings. You know, and this string was really for us a connection between applications or parts of the application. So what we have is we have an application that's kind of split up into two parts, for example, or many parts. And the so-called string is the link between the two. And the notion of a link shows up at many different levels. But of course, in a network, we're going to have links everywhere. So it's worthwhile spending a little bit of time thinking about what is a link anyway, and what is it? What are the properties of a link? So from the perspective of an application, if you're writing an application, let's say you're writing some game that's going to run on a smartphone, for you a link is just a way to communicate between two endpoints that have the network API. So you have this API, which is this, we talked about earlier, read-write API. So from our perspective, we have some application part and some application part over here, and then between the two is this interface, and then the interface allows you to send send data through what we've been calling a pipe. Okay, but as you know already, this pipe is not end-to-end. In fact, we have intermediate pieces along the way which actually make up that pipe. But nevertheless, from the perspective of the applications, we can talk about certain properties about this pipe. So one thing we can talk about certainly is what you can think of as reliability, or you can think of it as error rate. So what does it mean? It means that let's say I send a piece of information, a datagram. If you remember, datagram is a piece of data with a header on it, with header says this is where I'm supposed to go. So I put it into the pipe, and then one of two things could happen to it. One thing that could happen to it is that the bits inside could get messed up. So I might send a string of 1111, and what might come out of here may be 1011. And so what's happened is that along the way, some of the bits got flipped. Okay, so error of this sort is a 0 becomes a 1, or a 1 becomes a 0, and that's called a bit error. So we can think of the bit error rate. And so we can characterize a link by saying, what is the probability, what's the frequency of this happening? What is the bit error rate, in other words, right? And as you can imagine, it has an acronym as well. This is BER, okay? And that's a bit error rate. So from the perspective of the applications, this is hidden, okay? When you write an application program, you're very unlikely to see these kinds of errors. So how do we get around it? What we do is that when we want to send 1111, we actually don't send 1111. We send something else, okay? We send something like 1111 3 times, for example. Okay, when you send this 3 times, what will happen is what you might get would be 1111, 1011, and then the receiver says, we're going to take the best 2 out of 3, and this one looks bad, so let's cross it out, and so you get 1111 after all. So what we're doing is we're using redundancy to compensate for errors, okay? And that's, in fact, that's the name of the game. In fact, this is the only way for us to overcome bit errors, is to add additional redundant information. And the whole enterprise here becomes, how do we determine the least amount of additional information we need to add so that we can recover from any mistakes that are created by the pipe? And this is the basis of what's called information theory, where we characterize the properties of the link, and then we characterize what are called codes. These are called codes, which overcome these bit errors. But we won't talk about information theory here. just point out this is what people do. So that's one property of the link. Clearly is error rate. It's a bit error rate. A second kind of error happens because you send the packet. You may send 2 or 3 packets. Let's call them 1, 2, and 3, or probably 1, 2, and 3 in this direction. And let's say not all are received. Maybe only 2 gets through, or maybe 1 and 3 get through, but 2 does not. So you get 1, you get 3, but 2 is lost. And that's a packet loss. And if I send 1,000 packets, and let's say 5 of them get lost, we can say the packet loss rate is 5 over 1,000. So we have a packet loss rate. So we can characterize a link by a packet loss rate, right? So in the first case, the packet got through, but what was inside it got messed up. In the second case, the packet didn't get through. It's like you're sending a bunch of letters to the postal service, and one of them or several of them didn't make it. So how do we recover from this? Any suggestions? Yeah? Send multiple copies of the packet, right? So you send multiple copies of the packet exactly in the same way. So you can say, well, you know, this one drops packets, so I'm just going to send 2 of everything. But you can be cleverer than that. And the cleverer way of doing things is to send a packet over from here to here, and then ask the other side to say, hey, I got it. It's got acknowledgement. So you send a packet, get acknowledgement, send a packet. You don't get acknowledgement. You say, OK, I'm going to send it again. So then you only send those packets again that you suspect having lost, and that's what's called retransmission. And we'll study retransmission in great detail later on. But that's how we deal with packet losses. So in fact, the internet does deal with both bit losses and packet losses by using appropriate technologies. From the perspective of the application layer, when you send something in, we have underlying GUI over here called TCP, which makes sure that these things are taken care of. So when you send something, almost surely, unless something really bad happens, it's going to get to the other side. So that's reliability. Okay, so we talk about, so from the perspective of the TCP layer, beneath it, it's unreliable, but above it, it makes it reliable. So what we're doing is we're adding a service of reliability on top of an unreliable link, and that's how we build networks. We start with something which is not very nice. It corrupts packets, and it also drops them, and then we add some functionality, and then we export above us, transport layer exports above it, the virtual link, which is very nice and clean. If you send something, it's going to get there. It won't have any mistakes in it. Okay? And that's how we build these networks. And we'll study more about that. Okay. Any questions about this so far? OK, so that's one property. Let's talk about the second property. The second one is throughput. And the throughput is basically how many packets per second can I get across from one to the other, right? So if I send, it's intuitively speaking, let's say you're at home and you're running your, you're watching YouTube, right? And you're watching some particular video. And what happens is that you're receiving something, and then there's a pause, and then the video stops, and then it waits for a while, and then it continues again. What happened? Right? What happened was that you got some data, and then there wasn't enough throughput to sustain the video stream, which requires a certain number of frames per second, and so you had to wait for stuff to come through. So intuitively, we understand what throughput means. So it's basically how many packets are coming through this pipe per second, right? Another way of thinking of throughput is imagine that you're in an airport or a mall or something with an escalator, right? You have an escalator. So the escalator takes people in and it pushes out. So let's say there's a step on which 3 people can stand. So every step is going to give you 3 people. Okay, that's the throughput rate, 3 people per step. And that's what we call throughput in the network. How many packets are delivered per second? Okay, the higher this is, the better the connection in some sense. Okay, so when you get Rogers says we have 20 megabits per second, that actually is throughput. Okay, it's telling you. Often in computer networking, we use the word bandwidth instead of throughput, but actually bandwidth is completely the wrong term. It's not correct. It's a misuse of the term bandwidth, but throughput is the right term for it, and it's how many packets per second you're getting through. So we can characterize a link by that, right? So if you have a link which has a low throughput, you really can't do very much with it. You can't have applications that require a lot of throughput. So if you have a dial-up phone connection, which is fairly low bit rate, fairly low throughput, you can't really do video on it. But if a high-speed connection, a broadband connection, you can watch video on it, right? So we have this notion of throughput. And we can measure that. So we measure that as packets per second or bits per second. And bits per second is more accurate because packets per second are the packets of variable size. So it really doesn't make too much sense to say packets per second, but bits per second, well, that's more reasonable. OK, so moving along, the third thing we can use to characterize things is the delay. So delay says, if I put a packet in here, how long before it comes out to the other side, right? So I want to know that. Let's say I'm talking to somebody in a video conference. So when you talk, you'd like to have the other person listen, fairly soon, not after 5-10 seconds. Has anybody had the experience of talking on a connection where there's a very long delay? So you say something and it takes a long time for the other person to hear stuff. And it's frustrating, right? And it's frustrating because what happens is you say hello and you think they don't hear you and you repeat it. And then what happens almost is that you have two conversations going on, right? Where you say something and then they're responding to what you said earlier, but you already got the next one going. And it's really, really, because we're not built that way. Our brain doesn't expect this to happen. So we are very sensitive to delay for voice and video communication. And so we don't want that to happen. But delay is, in some sense, unavoidable. Okay, so where does the delay come from? It comes from different parts. One comes from speed of light, propagation delay. And the other one comes from, you can think of it as queuing delay. And the third one comes from link capacity, link throughput. Let me explain all those in just a minute. Okay. So the speed of light propagation delay is the easiest one to explain. The speed of light, as we discussed last time, is 3 × 10⁸ meters per second, and it's just not fast enough. Okay. And what I mean by that is this. The human response time, when you want to talk to somebody and have an interactive conversation, the end-to-end delay shouldn't exceed about 250 milliseconds, 1/4 of a second. Roughly speaking, it's what it is. If it's more than 1/4 of a second, it doesn't feel good. Okay, it feels unnatural. 250 milliseconds is about the time it takes for light to go around the Earth. Okay, just about that much. So if you go around the Earth, so if you make some, if you don't have shortest path routing, if you have a bit longer routing, what happens is that the speed of light propagation delay can be quite long, can be significant. It can be 150 milliseconds, 200 milliseconds, right? If you're talking to somebody in China, which is sort of antipodal to us, we have about 150 milliseconds of one-way delay just for speed of light. That's quite a bit, right? And so that's one element of delay that we really can't do much about. Okay? It gets worse when you try to talk to satellites that are out in space. So if you have something in geostationary satellite orbit, it takes 250 milliseconds to go up and 250 milliseconds to come down. So just up, down is half a second. So already you have bad voice quality. So anybody who's made a call on a satellite phone, okay, which is going through a geostationary satellite, will realize that the speed of light isn't fast enough for human communication. Okay? When you start talking to rovers on Mars, it turns out communication to Mars is rather interesting. So if Mars is close to Earth, it takes about 4 minutes. But if it's on the other side of the sun, it can take up to 80 minutes. And if it's, of course, blocked by the sun, there is no link. Okay, nothing goes through the sun. Okay, nothing goes through the sun. You can't send a signal through the sun. So you can have between 4 and 80 minutes. So you say something, hello, and then an hour and a half later it comes by saying, I just got beaten up by a dust storm. Okay, and in fact, this is what happens to those Mars rovers. So speed of light propagation delay is significant, and especially interplanetary communication, and but even terrestrial, it's a problem. Queuing delay. So we observed last time that when we have a shared link, the link may not be available, right? You go to a link, you say, I want to use it, and say, oh, sorry, somebody else is using it. So we have these intermediate points, which are also carrying traffic from other sources. So if that router is busy, it's going to say, hey, wait. And that causes a queue to build up. It's like going to the Tim Hortons. You don't get service right away all the time. You have to stand in line and wait in the queue. Well, so if you think about the time it takes for you to get a donut from the Tim Hortons, there's a speed of walking propagation delay. Okay, you got to walk there. You can't go faster than speed of light to get to the Tim Hortons. You may run there, but you can't outrun light. You have to wait in the queue, even if you got there, at 310.8 meters per second. You zip there, there's still a line, okay? Because the servers aren't infinitely fast. You got to wait queuing. But then you have another thing called the link throughput. And what the link throughput has to do is this funny coupling between delay and throughput. What it is that, let's say I have a large file to send, okay? Let's say the file is 10 to the 6 bits, okay? And let's say I'm sending it on a link which has 10 to the 3 bits per second as its capacity, 1 kilobit per second. Well, it's going to take me 10 to the 3 seconds, okay? And 10 to the 3 seconds is 1,000 seconds. 1,000 seconds is about approximately 20 minutes, right? So this 10 to the 6 bits is going to take me 20 minutes to send. That's delay, right? Because until I get the whole file, I can't do what I'm supposed to do with it, right? So that's the link throughput adds a delay. And this actually causes a lot of confusion in people's minds because they think that by improving the link throughput, you're going to reduce the delay. Yes and no, right? If you have a high speed link, a high throughput link, this one certainly is going to go down, but you're still going to be stuck with queuing delay and speed of light propagation delay. Just because you have a broadband link doesn't mean that China is any closer to you, okay? It's still going to take 100 milliseconds to get to China, right? Moreover, the link throughput only affects large packets. If you have a small packet, very small packet, that is primarily going to be influenced by speed of light propagation delay rather than queuing and link throughput delays. Whereas large packets are going to be primarily affected by the link throughput rather than queuing and, to some extent queuing, but certainly this is going to be the bulk of where the delay is coming from. So if I say I want a very low latency communication between the application endpoints, we can't really guarantee that because we don't know how far it's going. It may be going to Mars, right? What we're going to do about it, we can't do anything about it. On the other hand, even if it's close by, there may be a lot of queuing, but it's a very congested network. And even if there's no queuing, maybe you're just sending very large files and the link throughput isn't adequate. So because of these three reasons, we are kind of unable to kind of guarantee these delays. Okay, any other questions? Any questions for this? Okay, so I'll talk about a couple more and then we'll take a break. The next two are relatively easy. One is you can think of as security or privacy. Security is not the same as privacy, but I'm going to not make a distinction right now. We'll come back to the distinction about it later. But security basically means, are these links secure? If when I talk on this link, is what I'm saying going to be overheard? Okay, and there are certain links which are secure, right? There are these private banking links. Obviously, the link that's connected to your ATM to the bank, okay, you want it to be secure. You don't want random people to get in and say, give me money and whatever. So those are secure. But how do we do it? Again, the simplest explanation is that what we're doing is we're going to take these packets over here. What's sent over here is not the packets, but actually we scramble it up. We mess it up. And once we scramble all the bits, in some fashion, we send it over here, and then we unscramble the bits together. And then what comes out is what you actually send. So if anybody overheard it, then they're not able to make out what was sent. And so the scrambling and the unscrambling are controlled by what are called keys. And so what we do in the beginning is we exchange keys, saying, OK, I'm going to scramble it using this key, and this is the opposite. So I'm going to lock it up using this key, and you use the key to unlock it. And then in between everything, no matter if anybody hears it, it's going to be impossible for them to figure out what was done. So that's a cryptographic solution to a security problem. Okay, so So this can be done. So if you use SSH, as I mentioned, what you do there is you're going to scramble up all the communication so that whatever goes through is not going to be overheard, or even if it's overheard, it doesn't make any sense. Okay, so that's one. On the internet, unless you're using application level security or application level privacy, anything that's not encrypted at the application level is visible to the pipe. Okay, so anybody along the way can certainly tap in and listen to everything you're doing, and that's just the way, because it's too expensive in terms of performance to do this over here. Okay, any other questions over here? Okay, so let's talk about the last one, which is the cost. So the cost of a link is basically there are two costs to it. One is you can think of it as a dollar cost. How much does it cost per second, per minute, per month, per year? So you have to pay for it. And the second cost is an energy cost. And the energy cost is how much energy or how much energy does it take to use the link. So to be more precise, the energy cost is relevant mostly for mobile devices. So if you have a cell phone and you have two cell phones, one of them the battery lasts a week, the other one the battery lasts a day. Well, you probably want to buy the one that lasts a week. Why is the one that lasting a day not a good idea? Because it's using too much energy to communicate, right? So if you have exactly same usage profiles, if you are inefficient in your use of the system, the link is going to have a lot of energy cost to it, and so we want to avoid that. So there are many different tricks to avoid paying too much in terms of energy for links, for wireless links, and we'll touch upon some of those later on. But there is another way to characterize links, which is the cost, right? What does it cost you to do this? Okay. I think that's all I wanted to say about this. So one of the questions I had for the homework was how do these things interact? And I'd like you to actually think about it and see, are these goals compatible? Can I have a very cheap link which is also very reliable? Okay, why can't we have that? Can we have very cheap link or very high throughput and also have, say, high security? Can we have very low delay and also very low cost? Do these things go together? The short answer is no. Okay? There is no such thing as an infinitely fast, extremely reliable, zero delay, very secure, and zero cost link. There isn't one. Right? So we always have to kind of pick and choose which ones we want and then get the best that we can. Okay, so the question is, right, so the question is, what does pinging Google tell you about the delay characteristics of a game that you're going to play, right? So homework assignment 1 is actually kind of something I put together. It's an interesting assignment, I hope, because you'll get good sense of what does Google mean, okay, in terms of where is Google. And the answer is Google is everywhere, okay? Google is like Big Brother. They're everywhere. You're probably watching this video as well. Hi, guys. Okay. And it's in Google's interest to have presence globally. And so if your delay to Google is high, chances are pretty good that you're on an access link which has a high delay. Okay? And so you're not going to have a good success in any game, because if you can't get to Google, you can't get to anybody else either. Okay, so that's one way of thinking about it, right? So a ubiquitous service, if even that is going to be bad, then everything is going to be terrible. Okay. In the homework, you will actually find out the location for google.ca, where it is. You'll find the geolocation for it, and you'll find the path to it, and you'll see how long it takes to get to Google. So it's worth doing. It's also worth using some of the tools that are in the homework assignment to find paths to other services. So I chose Baidu, which is a server in China. It's one of the biggest search engines in the world. Actually, it's in Beijing. And you'll see how the propagation delays go up as you go to Baidu and come back. It's kind of interesting. And so anyway, but Baidu is not everywhere. Google is more or less. Okay, let me move on to come back to the World Wide Web, and I'm going to talk about cookies. So actually, the rest of the lecture is going to be hopefully quite a bit of fun, because by the end of this lecture, you should know a lot about how the web is put together. You should know about cookies and how Facebook works and how YouTube works and how Akamai works. So anyway, so I talked about the World Wide Web protocol, the HTTP protocol last time. I'm going to continue with a little bit more about cookies, and then I'll talk a little bit about the web structure. What does the web actually look like? Okay. So let me start with the review cookies again. So what are cookies? The way that the HTTP protocol is structured is that you have a client, which is your browser, and we have a server, which is your web server. And the client and the server are connected by some communication pipe, okay, which is a TCP connection. And it has certain properties in terms of reliability and throughput and delay and cost, which we'll ignore. We don't really care. From our perspective, what happens is that the client sends a request and gets back a response. And that's the heart of the protocol. You send a request, you get a response, send a request, get a response, and so on. Okay, that's basically what it is. The beauty of HTML is that the second request that you make or the third request that you make depends on the response. So the first request says, give me the default page, comes back, and then the next request you make depends on what response you got back. So that's how we get the hyperlinks. That's basically the idea of the web. Now, when the web was designed, it was meant to be what's called stateless. Okay, so what does stateless mean? Imagine you go to a restaurant, right? And you go in and you sit down, you have your meal, you come back, get home. And then you go back the next day and you do the same thing. You have the same meal and you come back. And you go back the third day and you have the same meal, same exact meal, and you come back. And the fourth day and the fifth day. And after about 2 weeks, the waiter sees you and says, yeah, we're going to order the same thing over. Let's just have the same old food for this person, right? What has happened is that by repeating the thing over and over again, you've established some state in the mind of the server, okay? Because you have a request, I want whatever. I want sesame chicken, you get sesame chicken. I want sesame chicken, I get sesame chicken. I want sesame chicken, I get sesame chicken. So there is this restaurant I go to where we always have sesame chicken. So we always make the same request. By the time we enter, they say, yeah, get the sesame chicken going because these guys, they never change. What has happened is that you have a state established on the server side. The server is the waiter. Imagine a system where the server has no state. So you go 10 years and you order the same thing every time, and after 10 years you go there and the waiter still says, what do you want for lunch or for dinner, right? It's sesame chicken, the same thing every time, but no, they are memoryless, they're stateless, they have no recollection. It's not a very nice restaurant, but that's a design of the web. The web was designed to be stateless. Okay, the server has no idea who came in. Once the response is over, it's as if they never existed ever before. And that's what we call a stateless service. Why is this important? It's important for, in the case of restaurants, when you have waiters who disappear. If you have a new waiter every day, well, obviously you don't want to have any state. But in the case of web servers, when they first designed were very flaky. They would die every few minutes. In fact, the Apache web server, how many people know what Apache stands for? Well, Apache is a very commonly used web server, and it stood for Apache web server. Apache meaning a bug fix. It was so buggy that they had to keep putting patches on it, like Band-Aids, to keep fixing it. And so they called it Apache web server. Okay, anyway, and because it kept dying, it was good to make it stateless. Now, let's roll forward to e-commerce, which was around 1998, 99, when Amazon came on the scene. They said, you know what, we want to do e-commerce, we want to remember our customers. How do you remember customers? What happens is that when the request comes in, you have some identification that goes with the request, which is, where did you come from, right? Initially, you just have a ID, which is your IP address, which is the address that you came from. You need at least that because you need to respond back to that. And the server says, I don't think I've seen this before. So along with the response, it's going to give a cookie, which is a tag. And the cookie says, OK, this corresponds to server so-and-so. And then the next request that goes in has the cookie in it. OK, so the browser, the client, makes this effort to first stored the cookie in a database. So this is supposed to represent a cylinder, and the cylinder is kind of a icon for storage, because hard drives were used to be in the form of cylinders. So this indicates storage. So what we're putting over here is the cookie. So the cookie comes over here, puts into store, and what happens is we're storing over here the cookie and the website, the web server address actually. Or a URL. So the next time you go to that same URL, what you do is you're going to give the cookie again. So what the server is doing is that server has its own store, which has the customer information and the cookie. So when this cookie comes back over here, it goes to the server and says, aha, this means this customer came back, and says, okay, I now know something about you. So it's like you go to a restaurant, and the first time you go, they give you a token. They give you this, like, they give you a cookie, right? And like a number. So you're customer number 24. So you go back in the next day, and you say, here I'm customer 24. They say, oh yeah, sesame chicken, right? Because that's what the database says. And that's the way that works over here. So at this point, now you have a response, but the response is now a customized response. Okay, so that's a customized response. Okay, so that's the way cookies were supposed to work. Okay, now can you read from the back over here, by the way? Yeah, okay. So what's going on here is that the definition of cookies was done to enable e-commerce, and it has a perfectly reasonable explanation. The problem is that it can be misused. So let me tell you two ways in which they can be misused. The first misuse is what's called third-party cookies. So a third-party cookie looks like this. Remember that the response over here is going to have a cookie in it. Now this cookie is supposed to be for the server. So let's say the server, for the sake of concreteness, is Amazon. Okay. So let's say the Amazon, this website address, it says Amazon on it. So I'm going to use my fancy colors here. So let's use this. So this one we say is Amazon. Okay. Now let's say that Amazon has a deal with a company that tracks where all the customers are. Okay. Let's call that company Google, just for the sake of argument. Or as it's also called DoubleClick, because DoubleClick was bought by Google. Okay. So what would happen then is that Amazon will make a deal with DoubleClick, and actually DoubleClick will make a deal with Amazon and CNN and CBC, you name it, all these companies, and say to them, please put on your website, okay, please put on it not just Amazon, but put in DoubleClick cookie. So what's going to happen? The response has the cookie from Amazon, which is in white, but it also has the cookie from Google or DoubleClick, like so, and they're both in your cookie site. Okay? So this is a third-party cookie. Now, why is it a problem? Well, the problem is that now when you come back to Amazon, you're going to say, well, I have this DoubleClick, so Amazon is going to tell DoubleClick essentially that you came back. But what's happened is, let's say you go to some other website, let's say you go to CNN. So now what happens is that DoubleClick is going to tell CNN, hey, put me down with CNN as well. So the cookie shows up here. So at this point, what happens is that DoubleClick knows that you're a person who goes to Amazon and you go to CNN. All right? And actually, they know more. They know exactly what you got at Amazon and what you watched at CNN. Right? Or when you go to CNN, on the side, you have an ad bar. That ad bar would contain an ad for Amazon. So if you're watching a news story on whatever, they would put the corresponding thing that you can buy from Amazon on the bar because they're tracking you. Okay, and this is done through third-party cookies. Okay, so to summarize, what's going on is that this entity over here, Google or DoubleClick, by adding these third-party cookies and making deals with the content providers, Amazon and CNN in this case, is able to actually keep track of where it is that you went, okay, because you have the same cookie from both. You can say, yeah. So what will happen is that the cookies contain both the Amazon cookie and the DoubleClick cookie. So DoubleClick says, okay, I have this cookie, your Amazon cookie, tell me what this guy bought, and then you're going to go put that over there. So that's the kind of deal that's happening on the back. Now, many people ban third-party cookies from their browsers. So about 40% of web browsers, you have a preference thing. You can say turn off third-party cookies, and many people do, 40%. What do we do for those 40%? We can track them still. And the way we track them, or the web tracks them, is not by using third-party cookies, but by using something else, which is advertising banners. And the way that works, so let me take this off for now. It's like this. So on the Amazon server, you have the home page, right? On top, there'll be an ad. Okay, some ad. It doesn't really matter what the ad is for. The ad is going to be served by DoubleClick. Okay. All right. So when that page has to be rendered, when that page has to be shown on the screen, the browser is forced to go to DoubleClick. So this browser over here is going to say, oh yeah, I need to show that ad on the top of the page. So I'm going to go and send the request. In addition to Amazon, it's going to send the request over here to DoubleClick, like so, and get a response back. And what it's going to do, it's going to put over here the DoubleClick cookie. Okay. And what the DoubleClick cookie is going to basically say is that I got somebody browsing to me from the Amazon page, because the ad is going to tell you. The ad says, here is the image that I want to serve from the ad, and that image is being served from DoubleClick, right? And so DoubleClick knows exactly where you came from. It came from the ad it put on Amazon, right? Because they customize the ads. So DoubleClick knows that somebody from Amazon with this cookie ID visited Amazon. What it then does is it puts a different ad with the CNN ad on it over here. So it puts an ad over here, and this ad, when it's served, also requires you to go to DoubleClick. Now your browser says, oh, I just went, I have the DoubleClick URL. What is my behavior when I'm supposed to send the cookie back? So I will. So it sends a cookie for DoubleClick back, and DoubleClick says, aha, somebody came to CNN, right, with my cookie. So they went to Amazon and they went to CNN, because this link over here, it has a referrer ID. Maybe I should. Okay. So when you get the ad, DoubleClick says, I got referred to by Amazon, and I had this cookie. And then when I got this one, I got referred to by CNN. It had this cookie. Okay. So let's kind of walk this through. Okay. So in the first step, you go to Amazon and you say, I want your home page. Amazon says, okay, here's the HTML for the home page. Oh, and by the way, there's an ad here. Okay. The ad comes from DoubleClick. And this is the URL for the ad. It's some complicated string. So the browser says, okay, it goes to DoubleClick and says, show me the ad. And the DoubleClick says, oh, that ad, I put that on Amazon. So you're coming from Amazon. I'm going to give you this cookie. I'm going to call you customer number 1. Put it in your database. You put in customer number 1, goes over here. Then you go to CNN. CNN says, oh, by the way, I have an ad. Okay, I want you to show the ad. You got to go to DoubleClick for the ad. So you go to DoubleClick, and the browser says, oh, I have a cookie for DoubleClick. I'm customer number 1, DoubleClick, show me the ad. So it shows you the ad, and it says, oh, customer number 1, that's the guy who went to Amazon. So what happens is then, is that for each customer, DoubleClick now knows every website you've been to that has the DoubleClick ad on it. But DoubleClick is not an ad that you go to. What DoubleClick is actually a consolidator, right? They are the back end behind hundreds of thousands or tens of thousands of websites who are advertising and are paying for behavioral information. Okay, so they're saying, okay, you, DoubleClick, please show car ads to people browsing, stories on auto shows. Okay, because they may be interested in buying cars. And DoubleClick finds out where you are browsing in Amazon or where you are browsing anywhere on the web, creates these very large databases of your behavior, and uses that to show targeted ads no matter where you go. And that's why you'll find that if you go read a news story or something, and you go to a website, you'll find that the ads are very much related to what it is that you browse for. If you go to ePinions, or you go to CNET, or any of these places which are customer review sites, you'll find that almost right away, the ads that are being shown to you will be relevant to what it is. And you'll get email from Amazon saying, oh, by the way, we're selling cameras or whatever it is that you browse. Because it's all being kept by DoubleClick, which is, of course, Google. Google bought DoubleClick about 3 or 4 years ago. So Google knows every search that you did on Google, every map location you looked up on Google Maps, every email that you sent on Gmail, every single friend you have on Google+. It knows every website you went through to DoubleClick, what you browsed on those websites, what you bought probably, if you use Google Cache, and any document you wrote on Google Docs. They know a lot about you. They know more about you than you think they know. Okay? And they are everywhere. So I don't use Google. I don't use Google Search. I don't use Gmail. I don't use Google Docs. I turn off DoubleClick. I don't have third-party cookies. I don't like Google. You can be free to do what you want, but I think Google knows too much about too many people, and I don't want them to know too much more about me than they already know. Yes, Tommy?
Would you say Google knows more about you than Facebook knows about you?
Facebook knows nothing about me. Absolutely zero.
Well, not you.
So Google. Facebook is very open about not caring about privacy. Facebook's business purpose is to ignore privacy and to provide free service in exchange for your private information, right? So it's like going to a grocery store with one of those cards. What do they call it? I don't know what they call it. Club cards. You get a discount and they know what you bought. Okay, it's a fair deal. I'm giving up privacy and my cat food is cheaper. Okay, I'm selling my privacy for money. Okay, it's fine. Facebook is doing the same thing. Obviously, Facebook is tracking everything you're doing, but you're very aware of it. Hopefully, Google is doing it, in my opinion, the sneaky way with these third-party cookies and this cookie tracking and stuff like that. And Google, of course, is open about saying that they do save everything. Everything that is ever done on Google since day one has been saved, and they're quite. They tell you that. So. After that, it's up to you. Yes?
I have one question. Maybe it's not that related.
Sure.
You mentioned they check on the cookies, right?
Yeah.
So I also remember last lecture you mentioned about the IP address.
Yes.
I want to know how exactly does the server read your cookie?
Okay, so the server doesn't read your cookie. What happens is that the browser, when it sees that you're going back to a web server for which it has a cookie, it will send the cookie with the request the second time around. It's not the server isn't doing anything, it's a browser that's doing it.
Okay, and then the server will update the cookie and send back a new one, right?
It can send a new cookie, it can keep the same cookie, but this cookie is sort of, it's up to the server to decide what it wants to put in there. It can update it or keep it the same. It can put expiry times on it and so on and so forth. Yes, over there.
Wouldn't ad blocker prevent DoubleClick from
Yes, it would. To the extent that ad blocker is effective at blocking ads, it would prevent your browser from going, yes, no script and ad blocker are things you should be installing just sort of, normally. Yeah. So websites are hosted on web servers, okay? And most of you have probably not thought too much about how these web servers organize. So I'm going to just show you like a very quick glimpse into how web servers are organized, and then we look at the high-end websites when Andy talks about data centers. So this is the graph that determines how the web works. On the x-axis is site popularity from the most popular site to the least popular site, and this is the number of hits to that site per day. And it looks something like this. Okay. So the top like 100 sites or top 1,000 sites, let's say, get like 99+% of all the hits. Okay, the top 1,000 sites, okay, top 1,000 most popular sites get almost all the hits. Okay, the remaining 10,000 first top 10,000 sites get something like 99.99%, and then everybody else gets what was left over. Okay, all the other sites get like 1 or 2 hits a day. Okay, so these guys on the top, okay, are architected to get to deal with very large volumes. For example, Twitter, which we'll discuss a little bit later, gets about 13,000 hits a second. 13,000 hits a second. My website, which is this great, beautiful site, gets 80,000 hits over 4 years. Okay. No, 5 years. So you can see that my site popularity is somewhere down there. Okay, and Twitter and Google and Facebook are up in the top 100. So the way the architecture is completely different, right? So the way the top gets architected is what's called a 3-tier architecture. And the way it works is that when you get in a request, you go into what's called a load balancer. And what a load balancer does is that it takes the load and just spreads it across a bunch of backends, because no single server can deal with 13,000 requests a second. So you get into load balancer. Load balancer is a piece of hardware. It's all it does is spread the load. It doesn't do any work. It just spreads it across. And so the request comes in. It gets sent to a bunch of these requests. And these are what are called the presentation server. Presentation servers. And what they're doing is they're actually going to show you the final HTML. Okay, so let's say you go to your homepage on Facebook, right? Think about it. Your homepage on Facebook has got hundreds and hundreds of elements in it. You have applications, you have pictures, you have other kind of content. All of it has got to be assembled together and made into HTML and then sent back to you, right? So all that has got to be done by this presentation server. What the presentation server does, it sends it to what's called it's often called a business logic system. So this one is doing HTML assembly. Business logic system is actually a server. There's again a whole bunch of these servers. And these business logic servers are essentially finding out from the cookies who you are, okay? What kind of stuff you need, what have you customized, what kind of stuff needs to be, essentially everything that needs to be done for you, but not doing the HTML, but everything else, all the logic, okay? You blocked certain people, you allowed certain other people. If you go to Amazon, there's like what you bought, what your shopping basket status is, all that stuff, all that is being done with business logic, and behind it is what's called the database tier. And so we have lots of databases over here. These are talking about, petabytes, so thousands of petabytes, exabytes of storage, lots and lots and lots of storage. So when you go to your, say, a Facebook page, the load balancer gives you to one of these presentation servers. The presentation server is going to give the request to a business logic server. It says, okay, this is some person. It retrieves your information, all the stuff that needs to be cobbled together, creates all the stuff that needs to be created to present, and gives a presentation and says, okay, this is all the stuff, now render it, make it into HTML for me. And by the way, put in whatever ads, etc. So the ads are going to come from some ad database, for example. And then the ad database is going to be pulled in and given here. So the presentation server assembles it all into HTML and gives it back to the load balancer, actually, and then back to the requester. Okay? So this allows all the amount of work that needs to be done to be broken up into different pieces. This one focuses only on storage. This focuses only on the logic of assembling what has to be done per customer, and this focuses only on the actual presentation, on HTML creation. Okay, just a minute. And so this scales forever. We can have sites that can grow indefinitely large by using this 3-tier architecture, and this is what's used for all the big servers. And these are all can be done in Apache. They can be done in IBM has something called WebSphere, which does this. And the programming is done using things like Ruby on Rails, using JavaScript. JavaScript would be here, or it'd be JSPs, and so on and so forth. Okay, so let me talk about small sites. So Medium is a different story altogether, which I'm not going to get into. I'll talk about the small ones, because those are actually quite interesting as well. In the small ones, what happens is that we have a server, and it actually hosts between 20 to like 4,000 sites on one single server. Okay, and these are called virtual servers. Over here, this is a virtual server. And the way it works actually is pretty straightforward. If you remember the host request, this request in HTTP has a line that says, I think it's called server colon, and then the URL. So you know that this server is being contacted for that URL. So you say, oh yeah, that URL, I'm going to give it to this virtual server to respond to. And so these are kind of microsites. You get 1 or 2, 5 hits a day. And these servers can handle 1,000 hits, maybe 100 hits a second, right? So you can pack these sites in. Now, each of these sites, you pay about $2 to $4 a month. Okay, so if you have 4,000 sites and you're paying $4 a month, you're making $16,000 a month on one server, and it costs you not very much to run it, right? So it's all profit. Okay, and so the biggest company of this is called 1&1. If you've seen ads for them, they're a German company, 1&1 AG, and they make money like crazy on this kind of thing because the prices are so low because you basically have no hits, you can pack them in. So I used to run a company in Silicon Valley. My students and I started a company, and we made software for web hosting. So we had 1 million sites hosted on our software. So I know how this works in extraordinarily great detail. There's a lot of money here because everybody is willing to pay, or any business is willing to pay $4 a month for a website which has no hits. Okay, so that was kind of web hosting from the 50,000-foot level. And so if you want to go get a website, you can, of course, you can either get a virtual website, like a virtual server. And if you do, there are many hosting providers out there, and you pay about $2 to $10 a month, or you can get your own server. You can actually go rent a server, okay, for $50 a month or so. And then you can run everything yourself. So that's for my research group, my website. Since I'm not commercial, I have a server in our machine room, and I run it. Except when my students break it down, it runs most of the time. And then the high end is when you get many servers. So you have many servers handling one website. So that was web popularity and how the whole thing works. I'm now going to switch gears and move on to DNS and tell you about this. In a bit more detail, and then CDN. Okay. The problem is I know too much about these things. I have to shrink it down. Okay, so DNS. Here's the problem we want to solve. Let's say you are expecting a child. You're having a baby. Your wife is having a baby. Your husband, whatever. Your family is having a baby, and you want that person to have a unique name. In the whole world, nobody else should have that same exact name. Okay, how would you do it? Okay, so here's one thing that you know. You know that at this exact spot on Earth, 2 babies won't be born at the exact millisecond. Okay, right? At the same exact millisecond and at the same exact 30 centimeter radius, you're not going to have 2 babies born, right? So you name the baby the latitude and longitude and the time down to the millisecond. Okay. Okay. So as long as everybody obeys this rule, you can be pretty sure that nobody else has that name. Okay. So I can choose this latitude, this longitude, and this time, and down to the okay. And as long as nobody cheats, it's unique. Okay. So that's one way to get global uniqueness. It's kind of a funky way to name children. Hey, 42 degrees north, 35. There is another way of doing it. Okay, so, yes, Siamese twins, but they're not born the same millisecond. Okay, one comes out before the other. It's physics. All right. There is a different way of doing it, which is less. What is assumed here is that there is a uniform way to refer to space and time, right? That time starts at the same 0 for everybody, and that space has the same coordinates. We don't have relative, but absolute coordinates for space. And strictly speaking, relativistically speaking, this doesn't hold. Einstein would come up with a way to figure out a way to have 2 people have the same quote-unquote time, the quote-unquote space. If you have a time warp and a black hole, you can actually do this. But if you're next to a black hole, you don't care about unique names anyway. You cannot die in the next second. There's another way of doing it, and I'll tell you how to do it this way. What I'll do is this. Let us say that I want to name my baby uniquely. I'll just choose some random name. So it doesn't, okay, I won't say random name. I'll just say name, which is the name. What I'll do is I'll precede it with my name, okay? And I'll precede that with, let's say, my father's name or mother's name, etc. And I can go back all the way. And then this gives me like a path in a tree, and hopefully that's unique, right? There will be many people whose name is Emma, which seems to be popular these days, but there's not somebody who's going to have the same, 12 levels of hierarchy the same. So if you have somebody 12 names long, it's going to be unique. And this is what happens in Spain, I believe, where they keep adding names till it grows beyond belief. So the other way of doing it is to do it like this. What you do is that you give people ownership over some part of what's called the namespace. So this kind of dotted thing is we call it a namespace. We give people ownership of part of the namespace. So, for example, there's somebody who owns .ca. So anything that ends in CA must go to a person who owns CA. Let's say we do that, right? So if you, and I'm talking about domain names for computers, not for people. But let's say babies are named with domain names. I could call somebody, mybaby.waterloo.ca. I mean, why not? And they would be very easily accessible on the internet. But I would go to the CA registrar, and I would say, look, register this name. Call something. Let's say UW or uwaterloo. Or uwat.ca. So I'm going to CA and say, I want uwat. If anybody else comes and says, I want uwat, you're going to say no. It's already taken, right? So if you do that, what the CA is going to do is going to delegate this name to you and say, okay, you are now the registrar for uwat. You're the registrar for uwat. And so let's say computer science comes to you and says, hey, I want CS. You'll say, fine, you get CS. I'll delegate anything inside CS to you, but I won't give CS to anybody else. And so if somebody else wants server 101, then server 101 goes to CS and says, I want server 101, and CS says, fine, you can have server 101, I'll make sure nobody else gets server 101, right? By having this system of registrars, okay, we get names that are human readable. They're not tied to any particular space and time like I had earlier. Not many levels of descendants either, but it allows CA to, all it needs to do is to make sure that nobody else, this is unique. It just has to make unique. It has to guarantee uniqueness in just the set of people who come to it. And we have sort of a registrar to enforce that. Similarly, uwat has to make sure that all the requests coming to uwat are unique. CS has to make sure everything inside CS is unique, and so on. And this creates what looks like a tree on its side, right? And in fact, the namespace is therefore called a hierarchical tree. This is a tree space, right? So if I give you a URL to make it more precise, let's say I give the URL image or image1 dot images dot google.ca, then this is some server. So we know that in CA only one company has Google. In Google only one server is called one set of servers is called images, and there's only one server called image1, right? So this is an image server that holds some image for Google and CA, and this is what we call a dotted. These are the dots over here, a dotted namespace, or the domains namespace. And so that's DNS, domain namespace. And as you can see, it allows us to actually have very long names if you want, okay? But they're all unique. Okay? That's how we get uniqueness. Okay? So any questions about this? So the three concepts that are important here, one is of hierarchy. So we have what we call a top-level domain. This is a top-level domain. And this is like .ca, .com, .edu, .info, .net, .org. These are, for example, the TLDs, the top-level domains. And recently, there's been many, many more that have been introduced. In fact, anybody is willing to pay $100,000 to the naming authority can get their own TLD, I believe, top-level domain. So we get that. And inside that, what we have is delegation. And the delegation says, okay, I'm going to transfer ownership of this part of the namespace. That means anything that has a suffix of uwat.ca, you got it. Nobody else is allowed to have that suffix uwat.ca, right? And so uwat tells the CS, anything that's suffix cs, uwat.ca, you own that. Okay? And that's how we get uniqueness, because each person guarantees uniqueness in their own little namespace, okay, in that subspace of namespace. And so the third, obviously, we have this notion of a namespace. Okay, so this is how DNS is organized. So far, all I've said is how we get unique names, but what is the purpose of the unique name, right? The purpose of the unique name is for us to actually do the translation from a name to IP address. So remember, so we have a name. So this is your DNS name, domain namespace name, and you want to go to an IP address. And the reason we want to do that is because there are many reasons, but one of them is that when we want to make an application level connection, right, the TCP level link, we have to give it an IP address. We can't give it a DNS name. We have to give it an IP address. Okay. So somehow we need to go from the name, like google.ca, to a particular IP address, and that translation is what is done by the domain name system. So domain name system, or DNS, is a protocol which allows you to do this translation. Okay. So you can think of it as a system where you go and you give it a name, and it says, here's the IP address. Okay. Now, there are a couple of reasons why I want to do it. One reason for doing it, so why translation? Okay. The first reason is it's easier to remember names. Right? I don't want to go to 179.28.32.4. I'd rather go to google.ca. So it's easier to remember. The second thing, it allows load balancing. And by load balancing, what I mean is that when you go to google.ca and you ask it for a name, it can give you a different IP address each time it's asked. So let's say that behind this name, google.ca, maybe there's 1,000 different IP addresses. So the first time somebody asks DNS, what is google.ca, it says the first address. The second time it asks you, it gives you a second address. The third time, a third address. These are all Google.ca servers but it's spreading the load across because all the requests are going to different servers, so that gives you load balancing. And third thing is gives you what's aliasing. And aliasing means that, let's say that image 1 is a server that you really don't want anybody to know about, and in fact, we want image.google.com. Maybe that actually, or image.google.ca maps to this. So you say to everybody, go to image.google.ca, but actually, this is where it's actually going to go to, and then that goes to an IP address, right? So we can take one name and replace that with another name, right? So this is useful because maybe you have, two companies, let's say Office Max and Staples buys Office Max. So somebody says, I want to go to officemax.com, and in fact, it goes to staples.com because they got bought out. They don't exist anymore. So we want for aliasing. So these reasons are good reasons why we want to translate it. And what the DNS, domain name system, does is to provide this translation from names to IP addresses, different IP addresses, or from names to names. This is a name to name. Okay. All right. So we'll stop here. I just realized that one of the homework questions again was I didn't get to cover it. So I'm going to edit Piazza, remove that question in the next 5 minutes. But we'll continue with this next time.